This is the next video in the chapter on chemical bonding and molecular geometry. We have just finished talking about ionic bonding, and now we're going to move on to the opposite, other kind of bonding, which is called covalent bonding. And we are going to start on the correct page, which says covalent bonding. Okay, so we have just talked about ionic compounds, which generally form from a metal and a non-metal. And here we are going to talk about covalent compounds. And covalent bonds form between two non-metal atoms. So that means they basically only occur between atoms that live in the p block. And we can also include hydrogen in that as well. So ionic is a metal and a non-metal. Covalent is between non-metals. The other difference between ionic and covalent is that ionic bonds occur between ions. The things that form the bond are charged. So ionic bonds occur because positive ions attract negative ions, that electrostatic attraction. Covalent bonds are different because covalent bonds do not occur between ions. They just occur between neutral atoms. So covalent bonds do not involve ions. And so the burning question that's probably on all of your minds is, why would atoms that aren't charged bother to bond at all? They're not attracted to each other. So why would they even want to be close to each other? So why would these atoms want to be near each other? Why would they want to be close enough to form a bond? After all, if we're talking about like charges repelling, both of these atoms have electrons, and electrons are all negatively charged. And if you bring them close together, wouldn't those electrons repel each other? Wouldn't that keep them from bonding at all? So electrons from each atom repel each other. And this is a definite disincentive to bonding. So if there's this reason not to bond, there must be a really good reason why bond should happen at all. And I can explain what that reason is using this plot. So we're going to make a plot experimentally determined with potential energy on the y-axis and internuclear distance on the x-axis. And internuclear distance just means the distance between two nuclei in two atoms. So the experimentally determined plot roughly looks like this. So it starts very positive, it decreases very quickly down to a minimum negative value, and then it returns back towards the baseline over on the right side. So we can kind of think of this plot as containing three regions. So I'm going to sort of roughly indicate them here. So we're going to call the one on the left region 1, the one in the middle region 2, and the one on the right region 3. And automatically, when you look at this plot, your eyes are drawn to this point, to the minimum. And that is indeed the most important point in the plot. That is the minimum energy, or the lowest energy position. And remember when we talked about electron configuration, we were always trying to find the configuration that had the lowest possible energy. And so indeed, in this situation as well, the atoms tend to orient themselves with a particular internuclear distance that gives the lowest energy configuration. So we're going to go rogue and start with region 3. It just makes more sense. So region 3, the two nuclei are too far. too far from each other to bond. So if you were to draw them, they would look like atoms that are super duper far apart, so far apart that they basically don't even notice each other. So in this situation, the atoms don't interact. And because they don't interact, that means the potential energy of the system is approximately zero. Nothing to see here, just two atoms on their own doing their own thing. And so that's not the lowest energy orientation in the diagram. The lowest energy orientation is in region 2, where the internuclear distance is just right. So what happens as we move those two nuclei closer and closer together is the electron clouds, which I represented by the circle, they start to overlap. And as they get closer, the electrons from one atom start to be able to feel the positive charge from the other nucleus because they're close enough together. And the electrons start to spend time, part of their time next to their own nucleus and part of their time next to the other nucleus. And that's a favorable orientation because the electrons are attracted to multiple spots and they can spend their time in a larger space. So electrons are attracted to both nuclei. And that really stabilizes the electrons in the system. That causes the potential energy to drop way down to a negative value, and that stabilizes the system. This is one of the core rules of chemistry. The lowest energy orientation is always the one that's most likely to occur. So as we move the nuclei closer and closer together, the electron clouds start to overlap, and at some point they reach a distance that's just right that gives the minimum amount of energy. If we were to keep going, if we were to push them, the nuclei, even closer and even closer together, eventually we reach a distance that is simply too close. And when this happens, those nuclei are so close together that the positively charged nuclei start to repel each other. Remember that those nuclei are very tiny, very dense, very highly positively charged areas, and they can feel each other's too. And if you move the atoms close enough together to each other, the nuclei will repel each other. And as you can see in the diagram, nuclei repelling each other is a very high energy situation and is not very stable. So that potential energy is a large positive number, and this orientation is unstable. Unstable and stable are just ways of describing whether the energy is going to be higher or lower. So on the left side, the nuclei are very close together. In the middle, they are somewhat close together, and on the right, they are not very close together at all. So let's add a few more notes to our picture. Atoms prefer the lowest energy orientation. And so that's why we choose region 2 to be the just right region, because that's the one with the lowest energy. And we'll find out later that this internuclear distance, the X value at this particular point at the minimum, that ends up being the length of the bond. And so when atoms go from not close at all to close enough to form a bond, the energy is decreased. And when the energy decreases, that extra energy has to go somewhere. And so that energy is released. And that is another important facet of chemistry, is energy is released when a bond is formed. You can think of this as taking two magnets and bringing them closer and closer together to each other. When they're close enough to make that bond or to attract each other, they jump together and you're barely able to hold them back. So it's a favorable transition and energy is released when a bond is formed. So this is the reason that covalent bonds happen at all, is because it's energetically favorable for those electron clouds to overlap and be able to circle around both of the nuclei. So in the next video, we'll talk about what the electron sharing, not sharing situation looks like in a covalent bond.